Okay, so we are going to look at a practice problem using Newton's second law for rotation and the concept of angular kinematics and Newton's second law. And it reads, a majorette, who's someone who twirls a baton, is holding her baton straight out with one end such that the baton is hanging straight down. The mass of the baton and the length of the baton are given here in this example, 0.6 kilograms, 0.7 meters long. With her other hand, she hits the center perfectly perpendicular to get that baton to start rotating. She hits it with 900 newtons of force for 3 milliseconds. And we want to know what is the angular speed of that baton immediately after she hits it. Now, this is a rotating object, and so we need to look at the rotational inertia of that object, of not only the shape of that object, the mass distribution, but the axis around which it is rotating. And so a rod rotating about one end has a moment of inertia given by 1/3 the mass times the length squared. So we'll utilize that idea for this particular object. All right, so we want to know how fast it's rotating right after she hits it. Well, that's a kinematics descriptor. And so we're going to start this problem looking at rotational kinematics. And to do that, we need to understand the object, that's of course the baton, and what we care about. So what defines our motion? When does it start? And when does it end? Well, it starts when she hits it. Okay, so we're interested in knowing what happens when she hits the baton, and then how fast it's going right after the hit. And because she's in contact with the baton, there is some kinematics happening during that contact time. All right. So what are our players of motion for rotation? Well, we don't know our angular displacement. That's not given. The baton is hanging at rest when she starts, so our initial angular speed is 0 radians per second. We don't know the final angular speed. That's what we're interested in. The acceleration, not given, but the time is 3 milliseconds, so 0.003 seconds. Now, we're interested in this final angular speed. And so we know that our final angular speed is equal to our initial angular speed times the acceleration times time. We know our angular speed initially is 0, so this term is going to go away. And if I then can know both my angular acceleration and my time, I can find my angular speed. All right, well, I'm given my time, but I'm not given my angular acceleration. Well, what causes an angular acceleration? A torque. So we know that the torque causes an angular acceleration related to that moment of inertia, that axis about which it's rotating, and of course the mass distribution. So if I want to find my angular acceleration, my torque divided by my moment of inertia should give me that angular acceleration. Well, the moment of inertia I'm given. I'm told that the baton has a mass of 0.6 kilograms and a length of 0.75. So 1/3 the mass of 0.6 times 0.75 squared is 0.1125 kilograms times meters squared. So I have my moment of inertia. I just need my torque. All right, well, when we need a torque, we do a torque analysis. So let's look at this object in an extended free body diagram to do a torque analysis. So there's my baton. What forces are acting on that baton, and where are they acting? Well, we know that the hand holding the baton is exerting a force, and by practice, I don't know what that force is. I can make some pretty good guesses. I know there's a force moving horizontally from her hit, so that hand must be causing, if the object is not translating, probably has a force in the horizontal direction. And I'm going to just put it backwards. If that's not the right direction, I'm going to be able to solve for that if I need to. And I also know that gravity's pulling it down, so I know there's going to be some vertical counter to that. So force of the hand also has a vertical component. Okay. I know that there's the force of the hit. So we have the force of the hit acting perpendicular at the center of the rod. That's given in the problem. We know that that's 900 newtons. And I also know that gravity's acting on this rod. It acts at the center of mass, and I haven't been told that this isn't uniformly distributed, so it's okay to make that assumption. All right, and I'm using the moment of inertia of a thin rod. Okay, so to do a torque analysis, I have to set a pivot point. Where am I going to set that pivot point? Well, I'm going to be strategic, and I'm going to set it at the hand because I don't have any idea what that force is. So if I set it at the hand, we know that the torque of the hand, both vertically and horizontally, are going to be equal to 0. They're at the pivot point. We also know that the torque of the force of gravity is 0. How come? Well, it's acting in line with the radius. And so there's no perpendicular component of that force, and therefore no torque being exerted by that force. So the angle is 0 degrees. So the only torque acting on this baton at the pivot point I have selected is the torque of the hit. And that, of course, is the force of the hit times the radius of the hit times the angle, sine of the angle. I got ahead of myself of the hit. So that's 900 newtons we're given. It's acting at half the length, so 0.375 meters, and it's acting at a positive 90 degrees. All right, so the torque given by the hit is 900 times 0.375 is 337.5 Newton meters. Okay, so I can now use this in my relationship for the angular acceleration. So I have 337.5 divided by 0.1125 is going to equal my angular acceleration, and that's 3,000 radians per second squared, which I can now use to solve for my angular speed. So my angular speed is 3,000 times 0.003, and I get an angular speed of 9 radians per second. All right, so recognizing we're interested in some kinematics, utilizing Newton's second law for rotation to find those kinematics, we had to do a torque analysis because Newton's second law, of course, talks about the torque acting on the object to get that angular acceleration. Good job.